It's exciting to see people. So I think we're ready to start now. Yeah? Okay, got the thumbs up. So thanks again for coming. On behalf of myself, I'm Elizabeth Fife, and my colleague Helen Choi here. We're from the Engineering and Society program, and we're the co-directors of the Communications Hub, which is the place for PhD students to get one-on-one help with all their critical writing and speaking projects. So today we have a very special event. This is Viterbi's very first 3-minute thesis contest. And this is a globally recognized event, and over 1,000 universities participate from all over the world. And the goal is to build students' academic and research presentation skills. So here are the rules. Basically, I won't go through all of them, but I want to keep it to 3 minutes. One static slide, 3 minutes max, and then you can go to the next one. The judging criteria has 2 basic categories. This is content, so significance, impact, that's clear. And then the second big category is kind of delivery related and sort of overall engagement, how well the talk is geared to a non-specialist audience and communication with spirit and enthusiasm. So we have exciting prizes, as you can see. Amazon gift cards for our top finishers. And then, again, we also have another surprise. Our first place winner will be sent to the regional competition in beautiful Portland, Oregon in March. So another exciting element to our competition. But beyond the prizes, it's really the learning experience that's really invaluable here. It's participating in the 3MT. It will just be part of the growing experience of each contestant's experience who are here. They're here to challenge themselves and speak in a public forum, and just by doing this, they should be congratulated, I think. So now I'd like to introduce our esteemed judging panel. First, we have Professor Tina Gregory from Viterbi's Information Technology Program, ITP. Next, we have Professor Bhaskar Krishnamachari from EE and Computer Science. And then finally, last but not least, we have Adam Smith, who's the Chief Content Officer from Viterbi Marketing and Communications. So now we have here the list of all of our great finalists. And at this point, I think we're pretty much ready to get going here. We have a few more audience members filtering in, so we'll let them come in. And we'll get going here. And first up, Haotian Hang. Come on up. Sure, of course. Yay. Here you go.
Thank you.
So take a minute.
Is the mic head pointing up?
It's already on.
No, you should clip it on yourself. Just make sure it's pointing up. Perfect.
It doesn't seem like there's much more room. You could maybe squish in and probably want to just sit on the floor, maybe? That seems more comfortable than standing. Yeah. You're young, you can sit. You can move up so there's more sitting room and space to escape if need be. Yeah. We won't need that. But. Yeah. Ready to go? Okay. All right. Our first speaker is ready to go here. This is Haotian Hang, and he's from the Department of Aerospace and Mechanical Engineering, and he's a third-year PhD student Advisor is Professor Eva Canso. His thesis is Control with Flow, Flow Sensing and Swimming Models Inspired by Fish. But his 3MT title is Control with Flow.
Can I start?
Whenever you're ready.
Yeah, hello everyone. Thank you for coming to my. It is not starting. Okay. Sorry. Hello everyone. Thank you for coming to this topic. And today I will be talking about control with flow. Designing an underwater vehicle which can navigate efficiently is a very challenging problem because lots of flow structures of different shapes and sizes are evolving with time. It is unrealistic to build a map ahead of time, and the environment is very different from what we are experiencing. However, we can get some intuition from fish, which have fascinating ability in sensing and interacting with those flow structures. Here, we divide the problem into two parts. The first part is the actuation of fish, and the second part is the sensing. Let's start with the first part. Fish have several different kinds of fins which can interact with the flow, in which the tail of the fish, which is the caudal fin, is playing the most important role. Here we simulate the problem in 2D. The black line represents the body and tail of the fish, and the red and blue line represents the flow structure generated by the swimming of fish. What we found is that when the active tail bit is in concern with the passive hydrodynamics, the swimming efficiency and the speed of the fish can be enhanced simultaneously. Moreover, the model we found which can generate the biggest benefit is matches the biological data. And the second part is the sensing of fish. Fish have fascinating ability in sensing the surrounding flow structures. They have lateral line system which locates on both sides of their body. However, how to utilize those local flow sensing information to help navigation is an open problem. Here we are considering a problem like this. This is a fish swimming forward, and another fish is swimming behind it. Its goal is to locate the leading fish. However, it cannot see where the leading fish is. What it knows is only the local flow field around it. Here we employ reinforcement learning to find a sensory control strategy through continuous trial and error. And we not only get a sensory control strategy which works very well and generalizes very well, but also we can interpret and understand the strategy. It locally drives the swimmer towards the region with higher flow speed, and by doing this, it can follow a zigzag trajectory like this to locate the leading fish. And these findings can not only help us in understand those biological behavior, which can help us better protect fish, but also it can also give us a lot of guidance in really designing an underwater vehicle. And that's all for my speech. Thank you so much. Oh, yeah.
Okay. Yeah, there's room.
Yeah,
you
there's
could
room
kind of
up here,
squeeze in
and
up
then
here,
we'll see.
and you could lean against that. A little, slightly more comfortable. And Yuanzhong, you're up. Yeah. Let's see the screen. I'll introduce you first. Okay, we're ready for our second speaker. This is Yuanzhong Pan. He's from the Department of Biomedical Engineering, fifth-year Ph.D. student. His advisor is Professor Steve Kay. His thesis is Pharmacological Targeting of Circadian Rhythm Genes in Cancer. His 3MT title is Fixing the Twisted Clock in Cancer.
Okay, good afternoon, everyone. My name is Yuanzhong Pan. I'm from the BME department. The title of my dissertation is called Targeting Circadian Clock Genes in Cancer. So what is circadian clock? The term circadian implies a 24-hour rhythm So imagine it's a clock in your body that tells you when to go to sleep, when to wake up, and when to eat. So there's actually a clock in each and every of your cells that tells your cells when to metabolize the junk food you eat and when to repair your DNA. And then, so how is this clock in your body formed? So like a real clock, they need some gears. The circadian clock, they use something called transcription factors that can form a negative feedback loop. If you're familiar with systems control, you know that a negative feedback loop gives you oscillation, and that's how the clock behavior is formed. And our labs and others have found that actually in tumors, they can take these gears, they can hijack those things to twist your transcription of your genes and promote their own growth. So, you have a twisted clock, then you have a growing tumor, which is a bad thing. But good thing we know about it, because out of the 2,100 genes we have, we know it may serve as a target to kill the cancer cells. So, so we wanted to target the tumor cells. In my dissertation, I knocked down the genes in the breast cancer tumor cells. I knocked down clock and found that the cancer cells died. This basically shows that clock is a target in breast tumor. So, but we cannot knock down genes in a patient because it requires some specific engineered HIV virus, and you cannot tell a patient that, oh, we're going to cure your cancer, but we're going to give you HIV, and you cannot sleep anymore. So we need drugs. So our lab has been developing drugs that target the clock for more than 10 years. We optimize the drugs to bind to the molecules we want to bind, and it can suppress the target gene of the clock. So we hope that if we use this drug, it can kill the cancer cells, and everyone can be happy ever after. So we use the drugs in the cancer cells, and unsurprisingly, we find that the drugs doesn't work. So the second half of my dissertation is to figure out why. Actually, clock is not the only genes that is used by the cancer cells. So I did some sequencing analysis and experiments and found out that clock, they're actually like real gears. They bind DNA to a specific location. So they require a certain group of factors to bind to DNA, a place called enhancer to to regulate the gene expression. So when we use the drug, it's not enough to halt the whole enhancer. So luckily, I found another drug that targets the proteasome that can target this whole enhancer and actually kill the tumor cells. So I hope that will earn my PhD degree. Thank you.
Just in time. Just in time. Great. Okay, our next speaker is Heramb Nemlekar from the Department of Computer Science. Heramb is a fourth-year PhD student. His advisor is Professor Stefanos Nikolaitis. His thesis is Efficiently Learning Human Preferences for Proactive Robot Assistance in Assembly Tasks. His 3MT title is Efficiently Learning Human Preferences for Personalized Robot Assistance. Take it away.
Hello, everyone. Most of us would have assembled some IKEA furniture like a table or a shelf. And I believe all of us do it a bit differently. Some of us like to stick to the instructions and follow every step, while others may want to skip a few steps, change a few things around. Me personally, I don't care about instructions. I just like to start doing it with the difficult thing, get it out of the way. You may want to start with the easiest one. So all of us have different preferences in how we build IKEA furniture. And similarly, in factories where workers build these large airplanes and satellites, they also have preferences in how they perform the task. Now, in these large assemblies, using robots to assist each worker can help them reduce their workload and also finish the task very fast. But because each worker can do the same assembly task slightly differently, they would need the robot to adapt and assist them in a way that is according to their personal preference. Now, current approaches require the worker or the user to show the robot, this is how I like to do the assembly, so that the robot can understand their preference. But as you can imagine, this process can be very tedious and time consuming, always having to show the robot what my preference is before the robot can actually assist the user. And so what I want to do is to make robots smarter so that they can infer or predict the preferences of these users. One way the robot can do this is by asking the user to start performing the assembly task and observe the first actions that they perform. So for example, in this model airplane assembly, say the user starts with assembling the propeller. What the robot can do is then compare the actions of this user to previous users who had done this same assembly task. And so if similar users who started with the propeller and the next step preferred to do the assembly of the main wing, the robot in this case can go to the storage, get the main wing, and give it to the user even before the user explicitly tells what their preference is. Another way the robot can efficiently predict the preference is based on how the same user had performed a different assembly task. So if the robot knows that, say, in a model car assembly, the same user preferred to start with the most difficult actions, the robot will then use machine learning to then predict that in this airplane assembly, the user will prefer to start with the most difficult actions as well. And so in this way, by predicting user preference, the robot can be a more intelligent partner to the workers and help the workers finish these large assembly tasks much more efficiently than before. Thank you.
The beep. Here you go, Mahmoud.
Okay, thank you.
Okay, let's try for the center here.
Okay.
Okay. Wait, sorry. No. I need to introduce you. Sorry, false alarm. Okay, so this is Mahmoud Abdelrahman, and he's from the Department of Electrical Engineering, third-year Ph.D. student. His advisor is Professor Dimitrios Christodoulidis, and his thesis is a thermodynamic description of highly multimoded nonlinear optical systems. His 3MT title is Thermodynamic Theory of Highly Multimoded Nonlinear Optical Systems. Okay, now you can start.
Okay. Good afternoon, everyone. Thank you for giving me this chance to talk about my research. First, I would like to start with an interesting effect in chaos theory called butterfly effect. Butterfly effect, in very simple words, means that the swing of a butterfly in Brazil can be the cause of a hurricane, for example, in Florida. This is well known in chaos theory, that any small perturbation that you may see it as negligible can cause very, very drastic changes at your output. So what is the relation of that in optics? In optics, we have our fibers. If you increase the power or the light input to our fibers, the fiber tends to be nonlinear. And when it tends to be nonlinear, it tends to be chaotic. And at this stage, it starts any small perturbation at the input start to make very large changes at the output. So the problem in environment, we have the thermodynamic theory, which can accurately describe the properties of the room that we have if we have the temperature and the pressure. But in optics, we don't have that. In optics, you have to simulate the fiber using Maxwell equation, and this can take hours or days. And if your problem is complex enough, this can take weeks. So what we wanted to do here is to use the principles of the thermodynamic theory in optics. How? Using maximization of the entropy exactly as the principle of thermodynamics theory. And let's try if it will work or not. What we did is that we maximized the entropy exactly like the principle of thermodynamics we know. And we compared our numerical data and analytical result. And it matched perfectly. After that, to verify more, we did experiments. And we found that the theory and the numerics match each other. So one may ask me, so what? What is the use of that? The use of that we now understand the physics. When we understand the physics of our environment or the atmosphere, we managed to make the refrigerator that we all have in our homes. So in optics, we will do the same story. We can do all optical refrigeration. So what is the use of that? The use of that is that if you have a very high speckled beam like that, you can convert it into very focused beam that you can use for cutting, welding, eye surgery, and all biomedical application. And that's what makes me passionate about optics, that not only we see it every day, but it has analogy of everything we have in our life. And thanks all for your interest.
Right to the wire. Rafa, here.
Okay. Right here, you mean?
About there.
About here, okay.
Yeah. Yeah, that's good.
All good?
Good.
Okay.
Okay, next up we have Mustafa Can Gursoy, Department of Electrical and Computer Engineering. He's a fourth-year Ph.D. student. Advisor is Professor Urbashi Mitra. Thesis is Engineering Nature, Bio-Inspired Molecular Communications. His 3MT title is Engineering Nature, Bio-Inspired Molecular Communications.
Thank you. I'd like you to imagine thousands or millions of tiny robots roaming around in our bodies, detecting diseases and fixing things on the spot. This rather futuristic idea is becoming more and more feasible every day with recent advancements in nanotechnology and biology. However, we also came to realize that these devices are very small on their own and they have very limited computational capabilities, so they need to communicate and cooperate to collectively do something bigger than their individual. When we think of communication, we typically think of sending and receiving radio waves over air or over cable. However, this paradigm is not applicable to microscopic settings, especially in biological systems. So what researchers have recently came up with is this new paradigm by looking at our own bodies and seeing each of our cells communicating with each other using chemical signals and leveraging this idea to establish this communication link. Unfortunately, this molecular communication paradigm is slow. And by slow, I mean very, very slow. So for frame of reference, our phones can handle sending or receiving millions and millions of bits per second, whereas molecular communications can only handle a couple of bits, and that is per hour. And the faster you want to go, the more reliability you start to lose. And that is exactly where my research comes in. I'm finding methods, rather a collection of methods that that make a framework together that can reliably communicate as well as increase the communication speed almost tenfold, and that is an order of magnitude, and still be simple that these tiny devices can handle them. This would hopefully yield to a lot of exciting applications. And for reference again, I'd like to go back to wireless communications once again. The difference between us only being able to talk on our phones and send text messages and this era that we have all these apps and YouTube full-on streaming and Twitch streaming and whatever you like is just an order of magnitude improvement in data rate. I'm sorry, just a couple of orders of magnitude improvement in data rate. So every single step that we take towards increasing this step is a large step towards enabling a lot of biomedical applications. And I'm excited about the future about this, and hopefully you are too. And thank you very much.
aim for around the middle there. Yeah. Okay, our next speaker is Arturo Cajal from the Department of Aerospace and Mechanical Engineering. Arturo is a 6-year PhD student, and the advisor is Professor Alejandra Uranga. Thesis is Modeling Laminar to Turbulent Transition in RAN Simulations. The 3MT title is Reduction of Fuel Burn and Aircraft Emissions.
When I meet God, I'm going to ask him two things. Why relativity and why turbulence? I'm pretty sure he will have an answer for the first one. Hello, everyone. My name is Arturo Cajal. I am a PhD candidate at the Aerospace and Mechanical Engineering Department. My research focuses in understanding how fluids interact with solid surfaces. And to do that, there's mainly two approaches. The first one is to do experiments in which we place a model into a water channel or a wind tunnel, and we study the different properties of the flow field around this object. And the second approach is to use computational methods to perform these experiments virtually. So my research takes the second approach, and I develop computational models to control the onset of turbulent flow to reduce drag. So to understand what is turbulent flow and what is drag, I'm going to use a couple of examples. So in the first one, imagine that you're in the middle of a pool, and at the beginning, this one is empty or full of air. And first, you're going to be asked to walk forward. You can do that with normality, without any challenge. Then we fill this pool with some water, and walking becomes a little bit harder. Finally, we change this water for some oil, and walking, it's harder now. So what's happening, this force that is not allowing you to move forward is what we know as a drag force. And this drag force is increasing because we're also increasing the viscosity of the different fluids we're using, air, water, and oil. But there's other methods in which the drag can increase, and this is if the flow is turbulent. So to understand what is a turbulent flow, let's go back into the pool, and at this moment, the pool is going to be filled with water, and you're going to be asked to keep your position, to stand still. First, water is going to start coming to you at a pretty low speed. You're going to barely notice it, and in order for you to keep the position, you need to put a little bit of energy. Later, the water is going to start increasing its flow speed, and it's going to start developing some waves, some chaotic motion, and this is turbulent flow. So in order for you to keep your position, you will need to input more energy, maybe even put your leg behind, and then hold the position, right? So the main takeaway from this example is that turbulent flow increases the drag. So my research focuses on developing computational models to control the onset of turbulent flow to reduce drag of vehicles burning hydrocarbon fuels. So in the example that I was using, we burn calories. But for aircraft moving in air or submarines navigating underwater, it comes from burning hydrocarbon fuels. So if we gain some control on this turbulent flow and how to reduce this drag, then we can reduce the environmental impact of different vehicles burning hydrocarbon fuels. Thank you very much.
All right, next up we have Ahmed Alzanki, representing Department of Industrial and Systems Engineering. Ahmed's a 7th-year PhD student, and his advisor is Professor Ali Abbas. His thesis is examining methods of assessing trade-offs in life and death decisions. 3MT title, Examining Methods of Assessing Trade-offs in Life and Death Decisions.
So hello, everyone. In everyday life, we are faced with a situation where we must make risky decisions among some options, or we can say alternatives. By risky decision, we mean when there's that option that has one outcome with a low chance of occurring, but if it occurs, it results in a huge loss. Of course, risky decisions are those where their outcomes lead to loss of life or death. So examples can be as simple as with those with low risk, when you decide to text while drive, you might incur a crash and thus leads to fatality. High-risk examples can include the decision to undergo chemotherapy for cancer patients, or at government level, pandemics. For how long should the government impose the stay-at-home order, taking into consideration saving lives without hurting the economy. So there is such a trade-off that you need to properly assess. So previously, the value of statistical life was used, a cost-benefit analysis, but I'm focusing on the concept of multi-attribute utility, where you can rank the alternatives that you have in terms of the hypothetical best and worst outcome. Then you can choose the alternative in terms of your taste of risk. So the first step in doing so is you have to conduct a factor analysis. You need to combine factors into less factors. So suppose you ended up with money and health. In terms of preference for money, I'm assuming everyone nobody wants less money to more. And I'm also assuming that for health, you would like to live more in a complete, healthy, happy state. So how do we structure that trade-off? Do we just state it explicitly, or we extract it from a certain way where we might just consider money alone or the health alone? So a behavioral experiment is conducted on a specific life and death decision to compare such methods and see which one gives consistent results, comparing the ease of use and complexity, and also to see how the decision maker can calibrate his thoughts. At the end of this experiment, the decision maker is being provided with a guidance on developing his own exchange rate of money and health. And we call it a micromode value, which is scientifically meaning it's the maximum amount of money the decision maker should be willing to pay to avoid 1 in a million chance of death. And this micromode exchange rate can vary. So,
That right in there.
Good job, Michelle. Good.
Oh, okay.
Move over just a little bit.
All right, next up we have Nripsuta Saxena from the Department of Computer Science. She's a fifth-year Ph.D. student. Her advisor is Professor Cyrus Shahabi. Her thesis is Towards a Fairer Society. Her 3MT title is Algorithms for a Fair World.
What does it mean to be fair? My research focuses on answering this question. This photo behind me is from a study by ProPublica, a nonprofit, who found an algorithmic tool used for making bail decisions is biased against African Americans. And yet this tool is still used in more than 40 states in the US. Why? Because this is where it gets tricky. The tool's outputs were biased against African Americans according to how ProPublica defined what it means to be fair. But according to the fairness definition used by the company that created the tool, it was fair. Here's the crux of the problem. How you define fairness can drastically change what kinds of outputs are allowed. Let's take a step back. How did we get here? Aren't computers and algorithms supposed to be less biased than us prejudiced human beings? The answer lies partly in how we train algorithms. We train algorithms on data collected from the real world. Our biases and prejudices get encoded in this data, and the models then pick up on them. That's how you go from biases and attitudes like boys are better at math and science than girls to targeted ad delivery algorithms on platforms like Facebook that deliver ads for well-paying jobs overwhelmingly to men. What does it mean to be fair? We've been grappling with this question for millennia, and in fact, many algorithmic fairness definitions borrow from philosophy. For example, one algorithmic fairness definition says to treat similar people similarly. That is, in essence, precisely what Aristotle said when he wrote, treat like cases as like. Designing fair classifiers is not easy. First, there is no agreement within the scientific community about what it means to be fair in what situation. Already, more than 21 definitions of fairness have been proposed. That's a lot. Second, assuming we somehow manage to get a consensus on what it means to be fair, in what context, we can still only correct for the biases we are aware of. It's quite likely we will have to constantly tweak these models as we recognize more harms and unintended consequences. My research places fairness constraints on algorithms to ensure the outcomes are fair. After running experiments, we found that the general public overwhelmingly prefers definitions of fairness that look at merit and equity. We utilize this knowledge to build algorithmic models that are fairer, more equitable, and help reduce disparate impacts, all in the hopes of creating a world that each one of us wants to live in. Thank you.
Yeah.
Not at the collar, just at the middle. Like in the middle there. Just downward. There you go. Is that good? Yeah. Okay, let me introduce you. Okay, next up we have Powen Yao from the Department of Computer Science. Powen's an 8th year Ph.D. student. His advisor is Professor Michael Zaida. Thesis is a virtual equipment system designing with hyperphysical user interface and whole body interaction in extended reality. His 3MT title is Designing a Virtual Equipment System for Virtual Reality.
All right. Hi, extended reality, or XR, refers to the different realities made possible by advances in computing, such as virtual reality and augmented reality. Sorry, I'm a bit nervous. These different realities are different from traditional desktop computing and your mobile phones in that they closely resemble the action, 3D action that you do in real life. So I stand in front of you wearing glasses from the future that supports XR. So you may think I'm presenting without assistance, but I'm actually seeing my speaker's notes and hearing my own commentary, thanks to my thesis work. My thesis work involves the design of a virtual equipment system, and we use two concepts to help with that. First is hyperphysical user interface. Given that anything is possible in virtual reality, we can have user interfaces that do not follow the laws of physics in our world. Second, we have whole body interaction. So even though you can do anything, at the end of the day, we, the user, are still here. So we need to design with the user in mind. With that, two qualities we have culminated in the work of a virtual equipment system with some interesting caveats. First, we can have nothing. We can have something from nothing. So I'm wearing this virtual headset, and you cannot see it, but I can. And I can also interact with it. So that brings us to a second point. I can do a variety of different actions, called gestures, to interact with this virtual equipment. For example, I can use my fingers to draw on it, much like you do with a mobile phone. I can also grab this and move it up and down to do a motion gesture. I can also grab it and say, hey, play my favorite music. And these different gestures can be associated with your headphone in its effect. So if I grab it, move it up and down, it can change the volume. Or it can advance to the next slide. Second, we have, let me see, from 0 to 1, PPS, peripersonal space. These equipments that we mentioned here is in our personal space, meaning next to our body. We can also have equipment that are in our peripersonal space, which means anywhere that I can grab. So I can have my calendar right here, and as I walk over here, I can always grab it right over here. Third, we can also make use of the, I think I skipped to the fourth. Fourth, we have we can make use of this the concept of dimensionality. So that imagine that there's a sphere here. If I grab it from this hand, I can grab a sword. If I grab it from this hand, I can grab a shield. And with that, I'm running out of time. This allows us to make use of the spatial sense and spatial memory. And so I
with you in the future. Thank you.
Next up, we have Patrick Gelbach from the Department of Biomedical Engineering. Patrick's a fifth-year PhD student. Advisor is Professor Stacy Finley. Thesis is genome-scale metabolic modeling of macrophages in colorectal cancer. 3MT title is mathematical modeling of immune cells in colon cancer.
Great. Thank you all for being here. So colon cancer is notoriously difficult to treat, not only because of the activity of the cancer cells themselves, but also the neighboring cells that make up what is called the tumor microenvironment. And one type of this cell that is involved in the tumor microenvironment are called macrophages, which are part of your immune system that is oriented towards defeating cancer and also foreign entities in your body. And these macrophages are cool because they can exhibit a variety of different behaviors depending on the context and depending on when you'd need your immune system to be active. But cancer kind of hijacks or takes advantage of that variation in the observed behavior of these immune cells and pushes these macrophages from an anti-cancer state towards actually supporting the survival and proliferation of the cancer cells. And we know a lot that difference in observed activity is dependent on how these cancer cells make and use energy, on their metabolism. But the differences in the metabolism of these pro-cancer or anti-cancer subgroups is not fully understood. And so my work has been taking patient data, integrating it into a framework that allows us to mathematically model the activity of the metabolism of these cells. And from there, we were able to separate out key differences between the pro-cancer and anti-cancer state, and we're actually able to predict interventions that could push could push a pro-cancer macrophage back towards its anti-cancer preferred behavior. But from there, we know the biology is a little bit messy, and that these macrophages don't fall neatly into these two large groups, but there's actually a gradient of behavior that can be observed. And so we extended our models to capture this cell-to-cell heterogeneity and identified the specific pathways and targets that allow for this progression from a pro-cancer state to an anti-cancer state and the opposite as well. And then finally, we extended these models to account for the interactions that these cells have with different types of cells that are also in the microenvironment. And so there are certain metabolic pathways that are used to work either in cooperation or against other types of cells in the microenvironment. And so we've identified through all of this targetable ways. First, we've fully captured the macrophage metabolism in these pro and anti-cancer states. We've accounted for variation across the population and then placed that understanding within the context of the entire tumor microenvironment. And so hopefully this understanding of immune metabolism can identify future work to develop new techniques to treat cancer. So thank you so much. Yeah, just good.
This is our final speaker.
Yeah, if you need to leave, it's okay.
Yeah, it's the final one. 3 more minutes.
3 more minutes.
We have a dog in the audience. Yay. All right, okay. Ready to go. So our final speaker, Kazem Bakian from the Department of Electrical and Computer Engineering. Kazem's a 6-year PhD student, advisor, Professor Mata Magajan. thesis, Microwave Instrumentation and Models for Studying the Subsurface Processes in Arctic Permafrost. His 3MT title is Microwave Instrumentation and Models for Studying the Subsurface Processes in Arctic Permafrost.
All right. Hi, everyone. As we're all sitting in this nice presentation and enjoying the 3-minute talk of everybody, there is something going on in the Arctic that is called Arctic amplification. In the past 40 years, the temperature in the Arctic has been increasing as much as 5 times faster than any other places on the Earth, such as Los Angeles. As Arctic gets warmer, ecosystem and earth scientists want to understand how the ecosystem is changing by the increase of the temperature. The most dominant feature in the Arctic is in the subsurface. It's a frozen ground that's called permafrost, and it stores the largest amount of organic carbon in the subsurface. As the temperature gets warmer, this frozen organic carbon gets thawed, and through the respiratory microbial activities in the subsurface, this organic carbon can release into atmosphere as greenhouse gases. So temperature gets warmer, permafrost gets thawed, and organic carbon released as greenhouse gases, and creates a cycle that's called permafrost cycle or permafrost feedback cycle. Scientists want to understand how this cycle is getting evolved, and at some point it gets unstable. To be able to do that, they need 2 information. One is the soil moisture, and the other one is soil organic carbon. One way is to go to the Arctic, which is fun, but it's a harsh environment, it's cold, and it's difficult to gather information on site. The other one is where my research plays in. I'm a radar scientist. Radars, I develop models and instruments that can be mounted on airplane, and these instruments can be fly over thousands of kilometers of the Arctic to measure the subsurface properties. I particularly develop models that relates the subsurface properties to the radar response. And through this models, I can provide the subsurface information that earth system scientists need, such as soil moisture and organic carbon, so that they can predict what would be the response of the Arctic ecosystem to the future. I have particularly developed instruments that can also be on other platforms, such as UAV, that can capture the macro topography of the Arctic environment. And we are hoping that as my PhD is finishing, the data that is available through my PhD can provide better understanding for the scientists so that they can understand the ecosystem dynamics in the Arctic better and better. Thank you.
We've learned a lot in 33 minutes, I think. So at this point, we'd like to do the People's Choice voting. So if you've got your phone, you can vote for your favorite speech, and then we'll take a little break for the final tabulations. We're ready to make the big announcements. The scores have been tabulated, and we'll start with the People's Choice Award, which goes to Nripsuta, Saxena. Congratulations. Nice job. A trophy. You have to sign something, so come back.
You're too busy. Oh, yeah. Take a picture. No, by yourself.
Congratulations. All right. So moving on to our third place finisher. In third is Heramb Nemlekar. Good job. Okay. Second place, Mustafa Can Gursoy from ECE. Good job.
Come forward, come forward, come forward. There you go. So you're.
Good job. And our first place finisher is Nripsuta Saxena. Nice job.
You got another one.
Another trophy.
Congratulations.
But congratulations to everyone who participated. You all did a great job. And we have certificates too first. And
Yeah, we will after. Yeah.
Yeah, great job.
Yeah.
Should I just Haotian, you're finalist. Good job. There you go. Yeah, we'll take one of everyone together too. Yeah. Yuanzhong Pan, come up and get your certificate. Nice job. There you go. Mahmoud Abdelrahman. Yeah, stay up here. We're going to take a picture, like a group shot. There you go. Good job. Arturo Cajal. There you go. Congratulations. Ahmed Alzanki. Yay, good job. There you go. You can stay up here.
Can you?
Okay, if you don't want to. Powen Yao. There you go. Congratulations. Patrick Gelbach. There you go. Good job. Kazem, Bakian. Yeah. All right. Yeah. And maybe first, second, and third, you can come up and we'll take a group shot. So thanks, everyone. Big congrats to all the competitors. Everyone who came. Thanks to our judges.
And we're having an event over winter break. So if you need a place to do your writing, come visit us at the hub.
Lunch provided.
We'll feed you.
Should we? Okay, thank you.